right, for anybody that's watching this online, I do want to apologize because it is Friday, Valentine's Day, and my class is, they're having trouble.
Yeah!
Eric Cheng. All right.
Why is the addition of X molarity to 0.0175 not negligible?
It is negligible. We're going to cross it off.
Oh.
Yes. Okay.
Wait, do you want to explain what happened
I
to
apologize
them?
because I didn't have this started when I should have. We were talking about the precipitation of barium sulfate. Can you see the board? If we take a solution that contains barium and a solution that contains sulfate, mix them together, they become more dilute because we're combining two solutions, and we find the new concentrations. We calculate the Q value with these concentrations. We find that Q is greater than K. So the reaction shifts back to the left. We assume that it shifts to the left completely, which is different because normally we just assume it goes back to equilibrium. We're going back all the way to completion based on the limiting reactant, which is Varium here. And then, so you see our ice table looks different than it usually does because we have an initial line that is right at the beginning. When it goes back to the left, then we start a new equilibrium initial line and just do an ice table from there the way we always do. So the barium, because it was the limiting reagent, was 0. The sulfate goes to the left the same amount that the barium does because they're a 1-to-1 ratio. So that was 0.025 minus 0.0075 gives us that concentration. The KSP for barium sulfate is 1.5 times 10 to the negative 9, which is equal to X times that term. Now this term right here, is X big or small?
Small.
Small. It's really small or just a little bit small?
Really small.
It's really small because it's a small little K value. So it goes to the right just a tiny little bit, meaning that that X is not going to add much to the 0.0175. So according to the 5% rule, we neglect that thing, and it's an easy calculation from there. When you solve for X, the question is what are the concentrations of barium ion and sulfate ion in solution? The sulfate ion we already know it's 0.0175. The barium ion is whatever the X is. So X is very simple. That divided by 0.0175.
So K is less than Q?
At the beginning, K was less than Q.
Okay.
That's why it did that shift.
Okay.
All right, so X, just so we have a completion to this problem, which may be the only thing we complete today, is 1.5 times 10 to the negative 9 divided by 0.0175. And that's going to give us 8.6 times 10, oh gosh, negative 8?
Negative 8.
Now that is the concentration of barium. Everybody okay with that? Yeah, you could try to add that to 0.0175, but this starts with all those zeros. That's not, it's negligible. It doesn't mean anything.
So that's what the solubility is then.
Yeah. Yeah. All right, so let's try another one now. Can you do this?
I don't think we can.
No.
You can do it.
Why do you have a teddy bear in your jacket? What is going on?
All right, we're going to try another one together. I'm not going to leave you to try this because you don't have enough focus today.
Yeah.
Who says who?
Felix.
So we have magnesium nitrate being added to sodium fluoride. And we were talking earlier this hour about how do you know what combination of ions could possibly make it precipitate? Well, you know that there's nothing with nitrate that's going to make it precipitate, and there's nothing with sodium that's going to make it precipitate, so the choice you make is probably going to be right. Besides the fact that it gives you the KSP of the one that's going to make it precipitate. Magnesium fluoride. So, let's do this problem the same way. And starting these problems, you have to get used to, because at the beginning you have one solution and one solution that you're pouring together. There's no precipitate at all there. But the chemical equation that we write assumes that there is, or it kind of implies that there is. magnesium fluoride, MgF2, is the only possible precipitate. Now you see something different about this problem that wasn't there in the last problem? The coefficient. Yes.
You're
All right.
writing that right across the glare
Is that hard to read?
on here, yeah.
Turn off the light.
That doesn't make any sense.
I'm going to make an initial line. It may actually be what we need to do. But if you just hold yours up a little bit, hold the iPad up so that we can see. Magnesium fluoride yields magnesium plus 2Fs. All right, that's good, Eamon. Now, in the initial line, what are the concentrations of magnesium ion and fluoride ion? Remember that these solutions are being diluted because we're combining two solutions together. So the magnesium ion concentration is not 0.01. It's less than that. What is it?
0.0038.
Thank you. 0.0.
So that's 0.0.
I don't remember that from last hour. 0.0038.
Wait, did you? No, you have to.
37. Yeah, that's what I remembered. I was just not remembering that 8. I'm going to go ahead and keep that in there, even though it's sig fig wrong. What was that?
Oh, nothing.
Okay. All right, so the fluoride concentration?
0.0625.
Do you have to do anything with the 2 right now?
Great question.
Wait, how's the mold?
How'd you do that?
Wait,
Don't you have to get the moles and then double it and then do?
wait, 150 to 1.
Yes, the final volume is 400 ml. So now you have your magnesium diluted not in, or dissolved not in 150 ml, but at 400 ml. So find the moles of magnesium, that times that divided by the total volume.
I got it.
That's how we get those. Yep.
Oh, it's a 1-to-1 mole ratio for the NAF. Okay.
And then modified ice table.
Okay, now hold on.
What?
The question is, hey, I see this 2 up here. Does that mean we need to double the concentration? No, don't fall into that trap. What is that 2 doing there? It's just telling the relationship between these 2 products. It doesn't mean you have twice as much fluoride ion.
Oh, wait.
Yeah.
Does that mean when you're, like, when you're finding which one goes to 0, that means you have to double the Mg that you're reducing?
However much of this gets used, twice that much of that will get used.
So just be X and 2X,
Yeah.
right?
Yes, yeah, it's going to be an X and 2X kind of thing. All right, now the first thing that we have to decide is a precipitate going to form? Calculate the magnesium ion concentration and fluoride ion concentration at equilibrium. Well, possibly it's just these. If they don't make any precipitate, then this is going to be what their concentrations are. But do you think it's going to make a precipitate?
Yeah.
Just take a wild guess.
Yes!
The Zoodles wouldn't be that nice to us.
Come on, look at that! It's 10 to the negative 9.
Yes, it does have a very small K value. So do you need to calculate Q, or do we just trust that it's going to make a precipitate? It's not even close. It's going to make a precipitate. So when they make a precipitate, we assume it goes to completion. So that's where I'm going to make this line like that.
The fluorine goes to completion, right?
Which one runs out first? No. You got 2 zeros. Here.
Oh, I didn't see that.
That's going to be the limiting reagent.
Jessica, Jerome's afraid of you.
That goes to 0. How much does that go down?
2 times.
Twice that much. Yes?
Yeah.
So 0.0625 minus 0.00375 times 2 is what?
Yeah, totally. Why are you guys laughing?
450, is that right? Oh, yeah, I was going to say I didn't remember that. Okay. Okay. So now we had 0 of that originally, but now we have some. We don't care how much, as long as we know we have some. It goes to completion that way, and then it's going to go back, dissolve, and establish its equilibrium.
X times X plus.
So if it goes to the right, that's going to be plus x. That's going to be plus 2x.
Is equal to.
And then at equilibrium, this is x, and that's 0.055 plus 2x. Is x going to be small?
Yeah.
Small enough that we can neglect the 2x term here? Yeah, now, when you have found the value for x, you might want to, just to make sure, multiply it by 2 and then see if it's less than 5% of that. It's going to turn out to be, by far.
Yes or
Yeah.
Why is it?
How come we don't square the .055?
How come we know what?
Because of the historic stuff.
We do.
Yeah.
We do square it. In the K value,
You subtract.
KSP is 6.4 times 10 to the negative 9. And that's equal to x times 0.055 plus 2x quantity squared. That's where it gets squared.
Oh,
Ah, you had it.
In the book, when we did our previous reading quiz, they multiplied the concentration by 2.
We had to multiply this, when this is going back this way, that goes down twice as much as that goes down. And that concentration gets multiplied by 2. The change in the concentration is multiplied by 2. I don't think the book doubled that. Or that term.
I got 2.1 times 10 to the negative 6.
For x,
Two point
Yeah.
1, 2.
x, which is the magnesium concentration, 2.1 times 10 to the negative 6.
Yeah.
Sounds good? Now what about the fluoride concentration?
You just double that, don't you?
No, 0.055.
Oh, well,
0.055 plus a really small number leaves you with 0.055. So that is our fluoride concentration right there. This is our magnesium concentration.
so hard.
What do you think of that? Okay,
Fast.
can I show you one more? It's not going to take long. It's easier than these two.
Okay.
Maybe another time.
We have like,
Maybe on Wednesday, so it'll be like good.
Yeah, you fools that aren't motivated, you're going to be so sorry.
No, we'll be motivated on Wednesday.
Yeah, right, you will. I'll have excuses then too. Oh, I'm so tired.
Oh, I'm so tired. I don't want
Yeah.
to continue right away. What's the chemistry?
Take a look at this problem.
I guess.
Aluminum hydroxide has a KSP of this really small number. At what pH
That's a
will a
stupid
0.2
number.
molarity aluminum solution begin to show precipitation of aluminum hydroxide? There is not this much work to do for this problem. In fact, I would say let's not even bother with an ice table.
Wouldn't it be like, no, like almost no OH would produce a precipitate
Yeah, it doesn't take very much, does it?
with a number that small?
Right, that's exactly right.
Okay.
Now, would you agree, if we want to show precipitation, that means that Q has to be greater than K? Would you agree with that? So if we know the concentration of one of these ions, the aluminum ion, let's see, Q is equal to the concentration of aluminum times the concentration of hydroxide.
Well, there is no precipitation.
Dude,
Q is there.
Now, if that number is greater than K,
there's no Q.
Is it cubed or not cubed?
yeah, it is greater than K. Sorry, it is OH cubed.
Wait.
Yeah, because it's there's 3 OHs there.
Yeah.
So we know the aluminum concentration is 0.2. We know the K value is given to us in the problem. So all we have to do is solve for the hydroxide concentration. That would give us the POH and then subtract 14 to get the pH.
It's a pretty low number, I'm guessing.
Yeah. Can you do that problem though? It's pretty easy.
So it has to be greater.
So if the problem's asking for concentrations, you got to go through the ice table and calculate concentrations. But they're not in this case. Well, it's kind of asking, it's asking for the concentration of one of them, just at the point at which it starts to precipitate. So all you got to know is what that value is. So if you do this, 0.2 times hydroxide, not OH concentration cubed is greater than 2 times 10 to the negative 32nd. Just solve for the hydroxide as long as it's greater than whatever number, then when you can find the POH and the pH to answer the question. Anybody have any questions about that?
That's 55.
Yeah, no, it's the same.
All right. I have something for you at the end of the hour here. Not food, no, I'm sorry, just writing somewhere.
Oh, yeah.
Am I recording?